In this section, we're going to talk about how vector-valued functions can be used to describe motion in space. So first, some definitions. If our vector-valued function r of t gives the position of an object, where that parameter t is time, then the velocity vector of the object is v of t equals r prime of t. So that first statement is just saying if we take the derivative of our position function, even if it's a vector function, that gives us velocity. And then our acceleration function is the derivative of velocity, or the second derivative of position. And since r is a vector-valued function, velocity and acceleration are also vector functions. The speed of the object is defined to be the magnitude of the velocity, so the magnitude of that velocity vector, which would be the same thing as the magnitude of r prime, and we learned earlier that's ds dt, where s is our arc length, or distance traveled along that path. So here's an example. For the function r of t equals ti plus 4 minus t squared j, let's describe the path of the object, find and sketch the velocity vector at the point 0, 4, and then we'll do the same thing for the acceleration vector. So first of all, for part A, to sketch the path of the object, I am going to eliminate the parameter. So x, the x component of this vector function is t, and the y component is 4 minus t squared. So then if x equals t, we can just plug that in to y equals 4 minus t squared, and we get y equals 4 minus x squared. I graphed that function in red at the bottom of the screen. It's a parabola that opens down, has a y-intercept of 4, so that's what I've drawn in red. Now, to complete this graph, I do need to figure out the orientation of the path, or the direction of the motion. And so I think the easiest way to do that is just to plot 2 points, and that'll show you what direction this object is traveling in. So for example, at t equals 0, if you plug 0 into those parametric equations above, you get x equals 0, y equals 4. And if you plug, let's go back, 1 in, you get x equals 1, y equals 3. So I plotted those 2 points, and then I can see that it is moving from t equals 0 to t equals 1. And so that shows the direction, or the orientation of that curve. All right, part B asks us to find and sketch our velocity vector at the point 0, 4. So I'm going to start by finding my velocity function, and I can do that by just taking the derivative of position. So my position vector is t, 4 minus t squared. Derivative of that would be 1, negative 2t. So there's my velocity vector. And then at the point 0, 4, we just figured out earlier when x is 0 and y is 4, that corresponds with t equals 0. So I just took t equals 0, plugged that into my velocity vector, and got the vector 1, 0. And then I'm going to sketch that on my graph at that point 0, 4. So in purple, I drew my velocity vector. Notice that the velocity vector is tangent to that curve. And then let's go ahead and find our acceleration vector. So I'm going to take the derivative of my velocity vector. That gave me 0, negative 2. And then, I guess there's no t's to plug in. So a of 0 is also 0, negative 2. And I'm going to plot that on my picture. There's the vector 0, negative 2. And so the acceleration vector gives us information about both how the speed of the object changes, as well as how the direction of the object changes. And so at this particular point, we can see that the direction of the object is definitely changing. And in fact, when you're at that maximum point, that highest point on the graph, the speed of the object is actually not changing, just the direction of the object. And so that's what that acceleration vector is telling us, is it's really telling us how the direction of that object as it's moving is changing at that point. All right, so as I just said, our acceleration gives us information about how both the speed and the direction of an object are changing. And sometimes it's useful to break that acceleration up into two components. One component that is in the same direction of the tangent vector, and another component that's in the same direction as the normal vector. And the component of your acceleration in the direction of the tangent vector, which we could call our tangential component of acceleration, gives us information about how the speed of the object is changing, whereas the component in the direction of the normal vector gives us information about how the trajectory is changing, how the path is changing, or the direction is changing. So I've got a bunch of formulas on the screen. So we're going to use the symbol a sub t to represent the tangential component of acceleration. And again, this tells us how the speed of the object is changing with time. We're going to use the symbol a sub n to be the normal component of our acceleration, and that describes how the direction of that object is changing. And so a sub t, our tangential component of acceleration, is defined to be the dot product of our acceleration vector with our unit tangent vector. And perhaps an easier way to compute that would be taking the dot product of velocity and acceleration divided by the magnitude of velocity. These two formulas that I just circled are identical because our tangent vector is the same thing as our velocity vector divided by the magnitude of the velocity vector. Earlier we learned our tangent vector is our derivative divided by the magnitude of our derivative, and so written in the context of velocity, it would be velocity over magnitude of velocity. So those two formulas are identical. And when we're computing this tangential component of acceleration, what exactly are we finding? Let me show you on a picture. So what I have drawn on the right side of the screen, the black is supposed to represent the path of the object. And then I put a purple acceleration vector. The blue is my tangent vector, the red is my normal vector. So the tangential component of the acceleration is that distance that I have shaded in green on the image. It's basically the magnitude of my projection of my acceleration vector onto my tangent vector. So the component of my acceleration vector in the direction of my tangent vector, that distance in green. And we can kind of see where this formula comes from just using right triangle trigonometry. So if angle theta is the angle between the acceleration and the tangent vector, then just using our SOHCAHTOA, or right triangle trig, we can see that that distance, a sub t, is equal to the length of vector a, so magnitude of a, times cosine of theta. I can also write that as, let me circle it, magnitude of a, magnitude of t, cosine theta, simply because t is defined to be our unit tangent vector, so it has a magnitude of 1, so multiplying by 1 doesn't actually change anything. And now what I have circled in green is actually our dot product formula. We learned that formula to be equivalent to our dot product, and so that's why our tangential component of acceleration is the dot product of a and our unit tangent vector, And so when we're talking about these components of acceleration, we're actually finding scalars. We're finding the length of that little green line segment in the picture. So then to find my normal component of acceleration, it's that distance that I've drawn in yellow. So you can do something similar with right triangle trig. I'm not going to do that in this video just to save time, but you can actually show that your normal component of acceleration is a dot n, and that can be written as the magnitude of the cross product of v and a divided by magnitude of v. And again, I'm not going to go through a proof here, but it comes from the fact that we had a formula for our magnitude of our cross product that involves sine of theta, and so we can arrive at this using the right triangle trig as well. All right, so that's our formula that I've circled in green for our normal component of acceleration. Although honestly, in most problems, I use this alternative formula. So if you've already found your tangential component, you can use the fact that we have a right triangle in this image. And so you could just use the Pythagorean formula. The fact that if you take your tangential component squared plus your normal component squared, that has to equal the magnitude squared. And so that's where this formula in purple comes from. It's just the Pythagorean formula. So we can say our normal component of acceleration is going to be the square root of the magnitude of acceleration minus our tangential component squared. I might have missed a squared when I was saying all that. But I definitely have it written down on the screen correctly. So let's do an example. Let's see how this works in an example. Let's find the normal and tangential components of acceleration as a function of t for an object with the following position function, r of t equals 2t, t squared minus 3t. So the very first thing I'm going to do is find my velocity function. And so I took the derivative of r of t. I got 2t, negative 3. And then I'll find my acceleration function by taking the derivative of velocity. So 0, 2, 0. I'm going to start by finding my tangential component of acceleration. And so to find that, I'm going to take a dot v divided by magnitude of v. So I'm going to go ahead and start by finding the dot product of a and v. And so I got, let's see, 0 times 2 plus 2 times 2t plus 0 times negative 3. So my dot product is just 4t. And then magnitude of vector v, I took the square root of 2 squared plus quantity 2t squared plus negative 3 squared. And that gave me square root of 4t squared plus 13. So there's my tangential component of acceleration, 4t divided by the square root of 4t squared plus 13. So again, this is the part of the acceleration that describes how the speed of the object is changing as a function of time. And so if our object were just moving in a straight line path, this would be our acceleration function. But because our object is moving on some curve through space, this is just part of the acceleration. It describes the part that impacts the speed of the object. To find our normal component of acceleration, I am going to use that second formula I gave you. I'm going to take the square root of magnitude of acceleration squared minus my tangential component squared. And that is just my Pythagorean formula, using the fact that the sum of the squares of the two components equals the magnitude of the acceleration squared. So plugging numbers in, I guess first of all, the magnitude of my acceleration vector, here's my acceleration vector. The length of that vector is just 2. If you don't recognize that, you could take the square root of 0 squared plus 2 squared plus 0 squared. Should get 2. But it only has one component, so length is 2, magnitude is 2. All All right, so then I'm going to take the square root of 2 squared minus my tangential component squared. I'm going to have to do a little bit of simplifying. So now I've got square root of 4 minus 16t squared over 4t squared plus 13. And then I went ahead and found a common denominator. So I got a common denominator of 4t squared plus 13 by multiplying 4 by 4t squared plus 13, top and bottom. And then I'll do the subtraction. The 16t squareds cancel out, and I'm just left with the square root of 52 over 4t squared plus 13. And you can just leave your answer like that. That's perfectly fine. I guess if you want to simplify it further, you can. 52 is the same as 4 times 13. So I guess you could write that as 2 root 13 over root 4t squared plus 13, but it doesn't matter how you write it. And so now I have a different function, and this is a function that describes how the position, or I'm sorry, I should say how the direction of the object is changing with time. All right, finally, we can use our vector-valued functions to describe projectile motion. And projectile motion is when you throw or drop an object and it eventually falls back down to the earth. And so when you either drop an object or throw an object up and let it fall back down to the earth, the acceleration of that object is only due to gravity. And so on the screen, at the top of the screen, when we have projectile motion, our acceleration function is going to be negative g, j. So our acceleration function points down in the y direction. It's just gravity pulling the object down. Assuming we're on Earth, if you're working with feet and seconds, you can use 32 for that g. And if you're working in meters and seconds, you can use 9.8 for that number g. All right, and then if the initial velocity of the object is what we're going to call v0, so that's a vector, and the initial position of the object is the vector r0, then we can use integration to find our velocity and position functions. So if we integrate our acceleration function, which was negative g, with a y component of negative g, we get negative gt, again, that's the y component, and then plus a constant. That constant is going to be our initial velocity. And then if we go ahead and integrate our velocity function, and that's what I have in the next line. So if we integrate our velocity function, integrate again, the negative gt becomes negative 1/2 gt squared. And then our constant v0, when we integrate that, it becomes v0t. And then our new constant is our initial position, r0. And so there's our formula for projectile motion. And if I actually want to write that formula in component form, so list out the components. At the top of the screen, I just copied down the formula from the previous slide. So we've got this negative 1/2 g t squared j, and then we've got our velocity vector times t, plus our initial position vector. So initial velocity, that v0 written as a vector. If the initial speed is scalar v0, theta is our angle of elevation, then that is going to be v0 cosine theta, v0 sine theta. That's the component form of that initial velocity vector. And if our object has an initial height of h, then our initial position vector is 0, h. So plugging those things in, finally at the bottom of the screen, there's my formula for projectile motion. It's a vector valued function where the x component is just v naught cosine theta t, and then the y component includes that component or that term that comes from gravity, so negative 1/2 gt squared, and then the plus v naught sine theta t, and then finally plus h, which was our initial position. So finally, let's finish this lesson by doing a kind of involved example, an example that has 3 parts of projectile motion, solving for some different items using the information we just learned. So my example says a quarterback releases a pass at a height of 7 feet. So initial height is 7 feet. And the ball is caught by a receiver downfield 30 yards at a height of 4 feet. The pass is released at an angle of 35 degrees. Okay, so our initial height was 7 feet. Angle of elevation of that pass is the 35 degrees. We are going to start by trying to find the speed of the football when it was released. And so the other information given to us is right here. The receiver caught the ball when they were 30 yards, or if we want to work in feet, which we should, 90 feet away from the starting point at a height of 4 feet. So that means when the ball was caught, at the time that the ball was caught, which I'm going to call T1, so at this time that the ball was caught, the position of the ball was 90,4. So 90 feet down the field, height of 4 feet. So let's use that information to see if we can find the speed of the football when it was released. So I'm going to start by just writing the position of the object as a vector valued function. So my x component of this vector is v naught cosine 35 degrees t, and then there's my y component, v naught sine of 35 degrees t, and then I use 32 for the g, so this is my negative 1/2 times 32 t squared. It's my gravity piece. And then plus 7 is my initial height. So there's my position function. And so based on the fact that the receiver caught it at the position 90,4, we know that at this unknown time t1, so when t is t1, the x component is going to equal 90, and when t is t1, the y component is going to equal 4. And so that basically allows me to write a system of equations. I have 2 equations with 2 unknowns, and so this is something I can solve. And I'm going to go ahead and use the substitution method to solve this. So I'm going to take my first equation, and I'm going to solve it for one variable. It doesn't matter which variable you solve it for. I chose to solve it for the t1 simply because my goal was to find the v naught. And so then if I solve it for t1, I plug that into my second equation, and then I'll have a bunch of v naughts, and that'll tell me the information I'm trying to find. Okay, so I took this first equation, the one that came from my x component, I solved it for t1. So t1 is 90 over v naught cosine 35. And then I'm going to take that expression and I'm going to plug it in for the t1s in that second equation, the equation that comes from the y component. And now this is something I can solve for v naught. And once I solve for v naught, I'll be done with part A. All right, so I just moved this over to give myself a little bit more room. First term, we can actually cancel those v naughts out, and we're left with 90, and then we've got a sine over cosine. So might as well just write that as 90 tangent 35. And then for the second term, I did 16 times 90 squared. That's where that 129,600 comes from. V naught squared over cosine 35 squared plus 7 equals 4. So then I'm trying to isolate the V naught. So I guess what I did is I took this fraction term with the V naught, moved it over to the right, and I guess the only other thing I did is minus the 4. So now on the left, I've got 90 tangent 35 plus 3 equals that fraction. And then I'm going to do some multiplying to try to get the V naught by itself. So I guess what I did is multiplied both sides by that denominator, that V naught squared cosine squared, and then divided by the 90 tangent plus 3. And so that's how I got V naught squared cosine squared equals that big number over 90 tangent plus 3. There we go. So there's my equation. We can just divide by the cosine squared. So I'm going to go ahead and do that. And then finally take the square root. And there's my final answer. The initial speed of the football has to be about 54.1 feet per second. Unless I put this in my calculator wrong. Alright, so all of that is part A. Part B is asking us to find the maximum height of the football. The maximum height of the football occurs when that football is no longer going up, when it's transitioning from going up to going down. And so we are at that maximum height of the football when the velocity vector has a y component of 0 and is no longer going up or down. So our velocity vector would only have the x component and would not have a y component. So if our position function, and I know the v naught now, so the 54.1, so I just plug that in. So our position function is now the vector 54.1 cosine 35t, and then minus 16t squared plus 54.1 sine of 35t plus 7. So there's our position function. I'm going to take the derivative of that, and that gives me my velocity function. So my derivative is 54.1 cosine 35, and then negative 32t plus 54.1 sine of 35. So I just took the derivative. And then finally, my maximum height will occur when that y component equals 0. So I just set my y component equal to 0, and then solve for t, and I got just under 1 second, 0.9697 seconds. So that's when the football has its maximum height. What is its maximum height? Well, I can just take that time, the 0.9697, plug it into my position vector, and the y component gives me the height. So the maximum height would be 22 feet. Finally, how long did the receiver have to get to the proper position to make the catch after the quarterback released the football? So back to that idea that at some unknown time t1, our receiver was able to catch the ball at a position of 94. This problem is actually just asking us, what is that t1? What was that time when the football had that position? And fortunately, we've done most of the work in part A. In part A, we had actually solved for t1. We said t1 has to be 90 divided by v naught cosine theta. That just came from setting our position function equal to that 94 at time t1. And in part A, we already found v naught. And so we can just plug that 54.1 in for v naught, put this into our calculator, I get just a little bit over 2 seconds. So the catch was made about 2 seconds after that ball was thrown. Right, that is it for this video. As always, let me know if anything is unclear.